Hi Year 12, this is the solutions to the 2021 Maths Extension to HSC exam. In this video I'm going to look at questions 11 to 13. Question 11a. The complex numbers z equals 2e to the I pi on 2 and w equals 6e to the I pi on 6 are given. Find the value of zw, giving the answer in the form re to the I theta. Okay, so just multiplying these, pretty easy question. We are going to get 12e to the I. We need to do pi on 2 plus pi on 6, which is 2 pi on 3. And just a quick check at the end to make sure that this is in the bounds. Remember, our argument has to be between negative pi and pi. And that is, so that's the answer. 11b, find the sum of I to the power of n from n equals 1 up to 5. Okay, so substituting in various values of n, we've got I to the power of 1 plus I squared plus I cubed plus I to the power of 4 plus I to the power of 5 equals I take away 1, take away I plus 1 plus I. What does this give us? I take away I, negative 1 plus 1, it is equal to I. C. Find the angle between the vectors A and B, giving the angle in degrees correct to 1 decimal place. So we want to use this formula. Cos theta is equal to A dot B divided by modulus of A and the modulus of B. Okay, so we want the dot product, so that's 2 times negative 3 plus 0 times 1 plus 4 times 2 all over square root of 2 squared is 4 plus 0 squared plus 4 squared is 16, and negative 3 all squared is 9 plus 1 squared is 1 plus 2 squared is 4. Right, let's just tidy that up a little bit. So 2 times negative 3 is negative 6 plus 8 is 2 over the square root of 20 times the square root of 14. All right, so theta is going to be inverse cos of all of that. Let's grab my calculator. I need to make sure that it is in degrees. It's not, it's in radians. So I shall change it. There we go. So inverse cos of 2 over square root of 20 times 14. Close the brackets. Degrees to 1 decimal place is 83.1 degrees. 11d. Find the two square roots of negative I, giving the answers in the form x plus iy. So I'm going to let negative I equal x plus iy all squared, which of course is equal to x squared minus y squared plus 2xyi. Now we're going to equate real and imaginary parts. Now of course negative I is the same as 0 take away I, so the real part of this number is 0. We'll start with the imaginary part though. So the coefficient of I is 2xy, and that's going to equal negative 1. Y is equal to negative 1 on 2x. And the real part, x squared minus y squared is equal to 0. Substitute this in. X squared take away negative 1 on 2x, all squared is equal to 0. X squared take away 1 on 4x squared is equal to 0. Multiply everything by 4x squared. 4x to the power of 4, take away 1 is equal to 0. And so x to the power of 4 is going to be equal to a quarter. So x will equal plus or minus the fourth root of 4, which is root 2. Now when x is equal to 1 on root 2, y is equal to negative 1 on 2 times 1 on root 2, which is negative root 2 on 2, or negative 1 on root 2. So our square roots will be 1 on root 2 minus 1 on root 2i, and negative 1 on root 2 plus 1 on root 2i. Part 2. Hence or otherwise solve z squared plus 2z plus 1 plus I equals 0. So let's do the quadratic formula. Z is going to be equal to negative 2 plus or minus the square root of 2 squared is 4. Take away 4 times A, which is 1, times C, all over 2. Negative 2 plus or minus the square root of 4, take away 4, I, all over 2, equals negative 2 plus or minus the square root of negative 4I over 2. Let's bring that 4 out of the square root. And those 2's will cancel out. Negative 1 plus or minus the square root of negative I. Now, we worked out in part 1 what the square roots of negative I were. Here they are up the top. So we have equals negative 1 plus or minus. Now, we only need one of these. 1 on root 2, take away 1 on root 2I. And just tidying those up, we get negative 1 plus 1 on root 2 minus 1 on root 2I. And negative 1 minus 1 on root 2 plus 1 on root 2I. E, the complex number Z equals 5 plus I and W is equal to 2 minus 4I are given. Find the conjugate of Z divided by W. Nice easy question. So 5 take away I on 2 minus 4I. Give your answer in Cartesian form, so we want to realise the denominator. And that gives us 10 plus 20I take 2I minus plus 4 all over 2 to the 4 take away negative 16 equals 14 plus 18I on 20. We have a common factor of 2. 7 plus 9I on 10. F. Express 3x squared take away 5 over x minus 2 in brackets x squared plus x plus 1 as a sum of partial fractions over r, and that's of course the real numbers. So we're going to let 3x squared take away 5 over x minus 2, x squared plus x plus 1 equal a over x minus 2 plus bx plus c over x squared plus x plus 1. And this, of course, is equal to a x squared plus 1 x plus 1 plus bx plus c x minus 2. Now, for space reasons, I'm going to drop the denominator. Hopefully that's okay. Therefore, this is equivalent. All right, we need to eliminate. Let's start with 2. Let x equal 2. So 3 times 2 squared is 12. Take away 5 is equal to a times 2 squared is 4, plus 2 is 6, plus 1 is 7, and this will all be 0. So I have got 12 take away 5 is 7 equals 7a. A is equal to 1. Now we'll let, we run out of room unfortunately, let x is equal to 0, and that will get rid of b. So we're going to have negative 5 is equal to a times 0 plus 0 plus 1 plus bx, that's gone, plus c times negative 2. Now we know a is 1. Negative 5 is equal to 1. Take away 2c. 2c is equal to 6. C is equal to 3. And then finally, let's let x equal 1. 3 take away 5 is negative 2 equals a times 1 plus 1 plus 1 is 3 plus b plus c times 1 take away 2 is negative 1. Negative 2 is equal to a is 1 plus c is 3, so this is negative b take away 3. That's gone. B is equal to 2. Therefore, it's going to be equal to 1 over x minus 2 plus 2x plus 3 over x squared plus x plus 1. Question 12a. Find the integral of 2x plus 3 over x squared plus 2x plus 2. The main thing we have to do in extension 2 integration is figure out which technique to use. So I'm looking at this thinking this might be log base e of this expression here. And if that's the case, I'm going to need the derivative of it sitting on top, which is 2x plus 2. And I've almost got that. So I'm inclined to think we're going to split this into two integrals, like this. 2x plus 2 over x squared plus 2x plus 2 dx plus the integral of 1 over x squared plus 2x plus 2 dx. Alright, so this one here is ln x squared plus 2x plus 2 plus, and this one here I'm going to complete the square. So it's x squared plus 2x plus 1, so that's x plus 1 all squared, and we have an extra 1 left over. Make sure that makes sense to you. So it's equal to ln x squared plus 2x plus 2 plus inverse tan of x plus 1 on 1 plus c. 12b. Consider statement A. If n squared is even, then n is even. Part 1. What is the converse of statement A? So remember, here's the premise and here's the consequence. We just want to switch them around. So the converse is going to be if n is even, then n squared is even. And then part 2, show that the converse of statement A is true. Alright, so let's write that down first. If n is even, then n squared is even. Alright, to show this, we're going to let n be an even number. So 2 times m, where m is an integer. Now n squared will equal 2m all squared, which is equal to 4m squared, which is equal to 2 lots of 2m squared. Therefore, n squared is even. C. Two lines are given by R1 and R2, and P and Q are real numbers. The lines intersect and are perpendicular. So let's start with perpendicular because I like it better. It means that 1, 0, 2 dot product with P3 negative 1 must equal 0. So P plus 0 take 2 is equal to 0, P is equal to 2. Now if they intersect, then they have a common point. So that means that negative 2 plus lambda must equal 4 plus P mu, and P is 2. Which gives us lambda take 2 mu is equal to 6. Second one, so the y coordinate, if you like, 1 plus 0 is equal to negative 2 plus 3 mu, so we can actually work out what mu is equal to, and 3 plus 2 lambda is equal to q minus mu. Okay, interesting. So we're here, from this one we've got 3 mu is equal to 3, mu is equal to 1. And therefore, from number 1, lambda take 2 is equal to 6, lambda is equal to 8. And solving down here, we've got 3 plus 2 eighths of 16 is equal to q minus mu, what's mu 1? Q is equal to 16 and 3 is 19 plus 1 is 20. D. Prove by mathematical induction that the square root of n factorial is greater than 2 to the n for integers n greater than or equal to 9. Right, step 1, prove it's true for n is equal to 9. So in other words, left-hand side is equal to the square root of 9 factorial, which is 602.395 ... The right-hand side is equal to 2 to the 9, which is 512. Therefore, yes, it is true, square root of 9 factorial is greater than 2 to the 9. It's true for n equals 9. Step 2. Assume it's true for n equals k. In other words, the square root of k factorial is greater than 2 to the k. Step 3. Prove it's true for n equals k plus 1. We are required to prove that the square root of k plus 1 factorial is greater than 2 to the k plus 1. Alright, I'm going to start with square root of k plus 1 factorial. Now that's equal to the square root of k plus 1 times the square root of k factorial. Now here's the thing. Square root of k factorial is greater than 2 to the k. So this statement here is greater than square root of k plus 1 times 2 to the k. Now have a look what we want to prove it. We want to prove it's greater than 2 to the k plus 1. So it'd be really great if this was equal to 2 times 2 to the k, because that's 2 to the k plus 1. But what is the value of this? The least k can be is 9. So when k is 9, we've got square root of 10, which is 3.1. And that's definitely greater than 2. So here's the logic. Because we've proven that our statement is greater than a thing that is bigger than the thing we wanted to prove, then this must be greater than that. So we've proved it. We will just say, therefore, square root of k plus 1 factorial is greater than 2k plus 1. Therefore, by process of mathematical induction, true for all n. I'm sure you'll write that better than me. 12e. The diagram shows the pyramid ABCDS. ABCD is a square. The diagonals of the square bisect each other at H. Show that the vectors HA plus HB plus HC plus HD equals 0. So what do we know here? We know that HA is the same vector as CH. And we know that the vector HB is the same vector as DH plus HC plus HD. Well, that's going to be equal to negative HC minus HD plus HC plus HD, and yeah, that does equal 0. Part 2. Using part 1 or otherwise, show that 4 times the vector GH plus the vector GS is equal to the 0 vector. So we're going to start by using what they have here, and we're going to leave the vector GS alone, but change these here. And this is a fairly easy question, because we can see that the vector GA is the same as the vector GH plus the vector HA. And similarly, GB is equal to GH plus HB all the way down, or etc., to GD. So if we take this here and we change it, we're going to go GH plus HA plus GH plus HB plus GH plus HC plus GH plus HD, I'm getting there, plus GS. Well, we know that that's equal to 0. And that's going to give us 4 lots of GH plus HA plus HB plus HC plus HD, we were told here, is equal to 0. So we've pretty much done it. Therefore, 4GH plus GS is equal to 0. And then finally, find the value of lambda such that HG is equal to lambda HS. So we had 4GH plus GS was equal to 0. So how do we get to here? We can see that we've got an HG and an HS. So we're going to do that same trick that we just did before. 4GH plus GH plus HS. So that's 5GH plus HS is equal to 0. We don't want GH, we want HG, so let's turn that around. And so 5HG is equal to HS. HG is equal to 1/5 HS. Lambda is equal to 1/5. Question 13a. The location of the complex number a plus ib is shown on the diagram. Indicate the locations of all of the fourth roots of the complex number. Okay, we have two things to consider, the modulus and the arguments. Let's start with the modulus, and that's the length of this vector here. All right, we can see that it is greater than 1, and it's not at 2. It might be something like 1.4. And if we do the fourth root of 1.4, we get a number that is bigger than 1, but it's not quite at 1.4, so it's somewhere in here. And that's going to be the length of all of our fourth roots. They're going to be outside this circle. All right, then we're going to consider the argument. Now this angle here is 4/5 of 90, which is 72 degrees. So let's set up an equation. Let's let z equal a cis 72. A, of course, is the modulus. We said it was approximately equal to 1.4, but we're just going to ignore that bit. So therefore, r cis theta to the power of 4, we want that to equal a cis 72. R to the power of 4 cis 4 theta is equal to a cis 72. 4 theta is equal to 72 plus 2k pi, where k is equal to 0 plus or minus 1, etc. And theta will equal 18 plus k pi on 2. Now we only need the first one, because as soon as we know one of the fourth roots, we know the rest of them are going to be separated by pi on 2, or 90 degrees. So 18 degrees is here. So this is our first complex number, the first fourth root. The second one will be up here, rotated by 90 degrees. Here's the third one. And then finally, whoops, I missed it, but never mind, there's the fourth one. 13b, use an appropriate substitution to evaluate the integral between root 10 and root 13 of x cubed square root of x squared take away 9 dx. Now with extension 2, they won't give you the substitution. And a basic rule is to try and get rid of that square root. So we're going to let u equal x squared take away 9. So du will equal 2x dx. This will be good because I can make, what's that, u plus 9. I can make this x cubed term out of this and out of this. In fact, I might turn this one around. Du over 2 is equal to x dx. All right. Let's do the limits. When x is equal to the square root of 10, u is equal to 10 take away 9, which is 1. When x is equal to the square root of 13, u is equal to 13 take away 9, which is 4. Right, we're ready to substitute. So it's going to become between 1 and 4. This x cubed is going to come from here and here. So it's going to be u plus 9 over 2. I'm going to put the du at the end, because I don't like to put it in the middle, doesn't make any sense. And then we have the square root of u, and then we'll have du. Alright, let's throw that half out the front. I'm just going to expand this out. This is u, because this is in brackets here. This is u to the power of 1 times u to the half, so that's u to the 3 halves, plus 9u to the half du is equal to a half. Integrate. Comes that, plus 9u 3 halves over 3 halves between 1, oops, that's meant to be a 4, and 4. And I'll spend one more second just tying this up. 2u to the 5 halves on 5 plus 9u to 3 halves times 2/3. Oh, this is horrible. Equals a half. Look, we've got to substitute in for both of these. 2 times 4 to the 5 halves over 5 plus 9 2 is 18 on 3. Oh, that cancels out. That's nice. 4 to the 3 halves. Take away 2/5 plus 8 on 3 is 6. Okay, and I'm going to put all of that into my calculator, so just bear with me a second. We are going to get 0.5 times brackets 2 times 32 divided by 5 plus 6 times 8 take away, brackets, 2/5 plus 6, close the brackets, equals 27.2. Hope that's the right answer. I'm sure it is. 13c. The integral in is defined as integral between 1 and e of ln x to the power of n dx for integers n greater than or equal to 0. Show that in is equal to e, take away n minus 1 for n is greater than or equal to 1. So we're going to use integration by parts, and remember, when we have a log involved, we're going to make this equal to u, and 1 is going to be v dashed. So let's set that up. We have u is equal to ln x to the power of n, u dashed is equal to n ln x to n minus 1 times 1 on x. And v dash is equal to 1 and v is equal to x. So in is equal to u times v, so x ln x to the power of n between 1 and e, take away the integral between 1 and e of u dashed times v, so n ln x to n minus 1 times 1 on x times x dx equals, subbing in e ln e to the power of n, take away log 1 to the power of n, that's 0, take away n integral 1 to e ln x n minus 1 dx equals, what's this, that's gone, e take away n, and that there is I subscript n minus 1. Question 13c. The diagram shows two regions. Region A is bounded by y is equal to 1 and x squared plus y squared is equal to 1 between x equals 0 and 1. Region B is bounded also by y is equal to 1 and y equals ln x between 1 and e. The volume of the solid created when the region between the curve y equals f of x and the x-axis between x equals a and x equals b is rotated about the x-axis is given by this formula here. The volume of the solid revolution formed when region A is rotated about the x-axis is v subscript a, and the volume of the solid revolution formed when region B is rotated about the x-axis is v subscript b. Using part 1 or otherwise, show that the ratio of volume of A to the volume of B is 1 to 3. So let's start off by working out the volume of A. So what we need to do here is work out the volume that's generated when we take this line y equals 1 and we rotate it around the x-axis, and then we're going to subtract the volume that's generated when we take this quadrant and rotate it around the x-axis. I'm actually going to join it all together. So let's see if this makes sense to you. So volume A will be pi in between 0 and 1 of 1 squared take away f of x squared, which in this case is y squared, and y squared is equal to 1 minus x squared. I'm going to put brackets in. 1 minus x squared dx is equal to pi integral 1 take 1 plus x squared dx is equal to pi integral x squared dx, which when we integrate is going to give us x cubed on 3 between 0 and 1, and when we substitute our limits in, we're going to get 1/3 take 0, so it's 1/3 of pi, which is pi over 3. Now let's work out volume B. We're going to do the same thing. Volume B is going to be this line y equals 1, rotated around the x-axis, so that volume, take away the volume underneath this curve, which is y equals ln x, rotated around the axis. So let's work out that formula. Volume B is equal to pi integral between 1 and e this time of 1 squared take away ln x all squared dx. Okay, we'll work out that first bit. 1 squared is just 1, and when I integrate I'll get x between 1 and e, take away pi integral of 1e ln x all squared dx, which is pi e take away 1 take away pi, and then using part 1 we know that this is going to be I2. Alright, where do we go from here? we're going to use our formula, take away pi. Have a look down here. So I2 is going to be equal to E take away 2I1 equals pi E take pi E plus 2 pi I1. I1 is equal to E take away 1 times I0. Okay, equals, cancel. We have got negative pi plus 2 pi E take away 2 pi I0. And I0 is integral between 1 to E of ln x to the power of 0, which is 1 dx, equals, what is this? Negative pi plus 2 pi E take away 2 pi, and in brackets the integral of 1 is x between 1 and E. Substitute in, we get negative pi plus 2 pi E take 2 pi E take 1, which is minus pi plus 2 pi E take away 2 pi E plus 2 pi. That cancels, equals pi. So the ratio of the volume of A to the volume of B is equal to pi on 3 to pi. I multiply both of those sides by 3 on pi, and I will end up with 1 to 3 as required. 13D. An object is moving in simple harmonic motion along the x-axis. The acceleration is given by -4 multiplied by x minus 3, where x is its displacement from the origin measured in meters after t seconds. Initially, the object is 5.5 meters to the right of the origin and moving towards the origin. The object has a speed of 8 meters per second as it passes through the origin, between which two values of x is the particle oscillating. Okay, let's have a look at what's happening here. So we know the center of motion is 3. We can tell that from here. Here's the origin. We know it starts at 5.5 and it's heading towards the origin. Now we're going to use this formula, v squared is equal to n squared a squared minus x squared, which is an incredibly useful formula and not given on your reference sheet. But because we have a different center of motion than 0, we need to change this part. So I'm just going to rub that out and put in x minus 3 all squared instead. All right, we do know a few things. We're going to use this pair of values here. V squared will be 8 squared, which is 64. We know n squared, it's here, so it's 4. A squared, that's the amplitude, that's actually what we're trying to find. X is 0, because it's passing through the origin, so this is -3 all squared. And 64 divided by 4 is 16, is equal to a squared, take away 9. A squared is equal to 25, and the amplitude is a positive number, so a is equal to 5, which means from the center, it's going to come all the way out to 8 and all the way down to -2. And they're the two values that the particle is oscillating between. Part 2, find the first value of t for which x equals 0, giving the answer correct to 2 decimal places. Now we are given these formulas here. I'm just going to do a quick sketch to see whether I'd like to use sine or cos. So we know the center of motion is 3, goes between 8 and -2, starts at 5.5 and heads towards the origin. So it looks something like this. So I think I'll use cos. It wouldn't matter if you used sine. So x is equal to, a is 5, cos, n is 2, plus alpha, and c is 3. Right, we need to work out what alpha is equal to, and we're going to use this information here. So when x is 5.5 meters to the right of the origin, t is 0. Subtract 3 from both sides. 5.5 take away 3 is 2.5, is equal to 5 cos alpha. Cos alpha is equal to 2.5 over 5, which is a half. So alpha is equal to 60 degrees, or pi on 3. And so that means that we have x is equal to 5 cos 2t plus pi on 3 plus 3. Now let's answer the question. Find the first value of t for which x is equal to 0. So we want to solve this trig equation. Okay, subtract 3 from both sides. I'll divide by the 5 at the same time. And so 2t plus pi on 3 will be equal to inverse cos of negative 3/5, which is equal to inverse cos of negative 3 divided 5, which is 2.214. Make sure you're in radians. 2.214. So 2t is equal to 2.214. Take away pi on 3 is 1.167. And then dividing by 2, I get, hopefully the answer, 0.58 seconds.